Hello, and welcome to Materials Unlocked, the podcast where we take a look at the lesser-known subject of material science and try to unlock its mysteries. My name is Dr. Lewis Owen, and I'm a lecturer at the University of Sheffield. In each episode, with the help of some students, friends and colleagues, we're going to delve into a particular topic and hopefully unlock its potential. So this week we're going to be talking about the materials design cycle and hopefully an overview of material science and what material science is and how it affects and shapes the world around us. As always on every episode, I'm going to be joined by a couple of our current students. And this week it's my very great pleasure to introduce Kavi Shama and Matt Turton. Kavi and Matt, welcome to the podcast.
Hello, Lewis.
Oh. So let's just introduce yourselves a bit. So Kavi,
First time ever being on a podcast, so it's going to be quite interesting. Like you said, I'm one of your final year PhD students doing material science on nuclear materials, which is pretty interesting.
Yeah. And Matt, how about you? What are you studying at the moment?
Well, I'm a second year PhD student and I'm investigating the local structure of high entropy alloys, again for nuclear applications.
Okay, so a high entropy alloy is probably something people haven't heard of before. So it's probably quite a complicated thing to be getting into very early in the podcast, but that's all right. We can talk about it. But it's a relatively new class of materials that lots of industry are quite interested in. So maybe we'll come back to that in a bit more detail later in the episode. So both of you are currently doing PhDs in material science, and as we said, you're both supervised by me. You have the great pleasure of being supervised by me. But were you both material scientists before doing a PhD? I think, Matt, you've been in material science all the way through, haven't you?
Yeah, I've been material science, did 4 years here at the University of Sheffield.
So why did you choose material science when you came to university?
Well, originally I wanted to do chemical engineering, and then I saw at Manchester Open Day the stall for materials science.
You saw the light and
and realised that was the part of the engineering that I wanted to do.
I think it's not uncommon. I mean, I was a chemist as an undergraduate and have now moved into material science, made that sort of slow transition over into material science, but have now is other. Kavi, what about you?
It seems I've lived the alternative life of Matt. I was a chemical engineer at Sheffield, and then I took a year out to work in battery science.
Right.
And then I came back to Sheffield to do material science PhD.
Okay, and now in metals rather than in battery materials.
Yes, definitely.
So slightly different.
The battery science did not go well with me. It was very slow-paced and very monotonous.
Yeah, it wasn't your particular cup of tea.
No.
Well, we're going to be talking about sort of material science in general and have a general overview. So we'll hopefully explore some of your experiences in the subject so far and talk a bit more about why you got into the subject and your particular interests. But we're joined as well by a specialist, Dr. Kathy Christofidou. Kathy, welcome to the podcast.
Thank you so much. It's so great to be here.
Now, Kathy, we have met before, is that right?
Just a little bit. Just a tiny bit.
So for the listeners at home, Kathy and I, we did our PhDs together. So we've known each other for quite a few years.
We won't say how many.
So it is many years. And now we run an academic group together.
We do indeed, yes. We run a group together called the Modern Alchemy Group that both Matt and Kavi are part of. And our sort of ethos for the group is that we put materials design and characterization at the very center of it.
Yeah. So where I thought we'd start, Kathy, is in your many hats and roles and things that you have in the university. One of them that you have is you're the admissions tutor for the department. And you and I have both been on open days talking to people like Matt, trying to sell material science and explain to them why chemical engineering is not the way for them to go and that they should come and do materials instead. When we talk to people, who are coming to the end of their school career and thinking about university and things, there's a lot of, I think, misunderstanding about what material science is and what it involves. So I wondered if you could tell us a bit about your sort of experience talking to people about material science and what they think it is and things like that.
Yeah, for sure. It's a really difficult one to explain to people, to be fair. Like, as a first starter for 10, a lot of people think that we're talking about textiles, for example, or a particular class of materials and don't really understand that there's a lot more to materials. In fact, materials is everything, from the chairs, the fabrics that our chairs are made out of, to the table and how it's constructed, to the airplanes that we fly on, and the nuclear materials that Matt and Kavi have been talking about as well. Everything is made out of materials. And to make things better, we need better materials. So you can think back to, I don't know, the Wright brothers plane that was made out of wood and some canvas. The principles haven't changed at all from that. And suddenly we've got, I don't know, the B-52 bombers or things like that are completely stealth and undetectable. All of that is down to materials. The fundamentals of how that works haven't changed at all. What's changed is what we can do with materials and how we can make things better.
Yeah, so I suppose one of the things that we take for granted is that we've always had just like stuff to make things out of. Like, you know, for years and years, we've had steels and, you know, bricks, concrete, all of these things. And we've always had sort of, as I say, just stuff lying around that we can manufacture something out of, make something for a particular application or whatever. But particularly, I suppose, now with those very high-end applications, we now need to think in great depth about, you know, exactly what's going into them and how we can make things for a particular, like, purpose and things. But
100%. I mean, if we think about it historically, we even name our historical eras after materials. There's the Stone Age, the Bronze Age, the Iron Age. Everything is defined by how we actually figured out how to use materials in different ways. We now live in the Silicon Age. I don't know what's going to be next.
Yeah.
And I think that's the really exciting thing about our sector in general, what we can do to make materials and realize technologies that never existed before.
Yeah. Do you guys find when you're talking to, you know, friends and family and explaining what you do, that you find it quite difficult to explain to them what material science is, and there's a lot of sort of misconceptions about sort of materials?
It is the most difficult thing to explain to people that don't know what it is.
Yeah, I find it more difficult than talking about my research, just to explain what material science is. I tried to explain it to my dad this weekend, and I just kept repeating the word material science over again, trying to click on how to explain it in a simple way that people understand. But it's very, very difficult.
So I think when you say something like with your research, if you say something like nuclear or something, people get a very clear image in their mind as to what that is. But with material science, there's just sort of nothing there. People don't necessarily have a touch. As Kathy says, you know, it tends to be textiles or something. They're like, oh, fabric, you know, cotton, wool, things like that. But it's so much more. It's so much more than that. So thinking then about materials design, Kathy, which you sort of referenced and things. So as I say, for years we've just had stuff around that we can make things out of. But how do we then sort of go about developing a new material? How do you go about like discovering something? Because when people talk about like, you know, thinking about slightly different field, obviously, but think about like, you know, Marie Curie discovering, you know, radium and things like that. How you go about designing a new material, I think is just very alien to a lot of people. And it's something that they probably never considered about how we would go about that investigation and studies.
It's absolutely true. Yeah, we sort of tend to always start with what we have around us, right? So if you think about an application, I don't know, let's think about the nuclear reactors that Kavi and Matt are working on. The first instinct is what materials might be suitable that currently exist. So we usually tend to start with something that we know and understand and is widely available. The next step is we put it into service in the application and realize, oh my God, that was a terrible decision. And we probably need to think about it in a little bit more detail. So we start understanding how our technology and our application develops and how the material behaves in that application. So from that point, we start defining what properties our material will have to have. So for example, does it have to operate at really high temperatures? That's a key factor. Not all materials can do that. Does it have to be resistant to, say, water or radiation in the case of the nuclear reactors? So we start bringing all of that together, and suddenly you don't have a material that meets all of those conditions. So we have to go back to the drawing board and understand how we can change a material or start completely from scratch to see how we can make something that meets all of those requirements, or where it is that we can compromise on those requirements. So it is quite alien, and the way that we do it, and that's the way that we still do it, we start with something that we know and we figure out that is not fit for purpose. And then we start the design process from how is it not fit for purpose and how we can make a material better to be able to apply it to that particular service condition.
Yeah, and there's that sort of gradual, you talk about properties and sort of thinking about the different properties that are required for a different purpose and things. And often when we're then making the materials, there's a sort of balancing act to be done between the different properties.
That's right. Yeah. We need to balance a lot of things. For example, if you think about metals, a lot of the time we want to use a metal because it operates at fairly high temperatures. But as it operates at high temperatures, it might get soft. It's one of the only materials that can operate at high temperatures, but it will get softer and softer and softer the more we use it. So we might want to figure out how we can make it harder at those high temperatures so that it can retain its sort of rigidity. So we need to consider what are our compromise points and how we can then tackle those compromise points going forward. So there's a related field, I guess, to materials design that is materials lifing, where we effectively use a lot of statistics and a lot of the physics-based models that we have to understand how long a material will last in that specific application. And usually we life it based on its weaker property, effectively. And that's a key factor that we use, particularly in areas where material failure might cause loss of human life, like the nuclear industry, like the aerospace industry.
I think there's also a misconception with how complicated it is to create an alloy, because some people think, oh, this material's hard, this material's soft, so if you mix them together, it'll make something in between, and then that'll be okay. And that's not always the case. You can't just mix.
It never is.
Yeah, it never is the case.
Things are never as well behaved as we'd like.
There's always a second reaction or a secondary phase or something that occurs within the combining of two things that you think should work together, and it never makes sense.
Yeah, nature has other ideas.
Yeah. So I think there's a misconception where it's easier just to mix things together. It just never works that way.
So in terms then of thinking, if we're thinking right from the beginning, okay, so you said that we're going to approach a problem and think about what the application is. So we choose a particular application that we might want to focus on. And then we have to go about working out what properties are required for that particular application. So I assume we therefore have to work very closely with engineers and, you know, people in the sector to understand those sort of responsibilities and things.
That's right, yes. And that's one of the really, really fascinating things about material science, because yes, we understand our materials incredibly well, but actually we need to be the best multitaskers of the engineers, because we need to be able to understand the nuclear engineers, and we need to be able to understand the aerospace engineers, and we need to be able to understand the chemical engineers and everybody's design principles. Because often when you say design, most people think about, oh, what are the stresses that this component is going to experience, or some other critical properties, for example, how much electricity do I need to get out of this particular component? So we need to be able to understand all the different areas so that we can understand their requirements and then design our materials to adhere to those requirements.
Which is actually, I mean, you know, I tend to think of material science as quite a sort of, it sits on those boundaries between a lot of fields, and actually it's very interdisciplinary in nature, and actually having different backgrounds, like coming from chemical engineering and things like that, sometimes gives you a slightly different sort of view of a particular project, or slightly different understanding, which is one of the reasons I find it quite exciting and interesting. Kathy, your background was aerospace materials, is that right?
That's right.
Remember that correctly. So yes, you came through materials sort of all the way through.
I did, yeah. I came through a material science and engineering department, and I did a little bit of a double major almost in some cases, because we were doing a lot of the fundamentals of aerospace engineering, things like structures and fluids and all of that, and aerodynamics.
So to give that understanding of what is required then for the properties, so you can then sort of, you know, have that understanding, yeah.
Exactly, yeah. And then from there, we build on the materials sort of side of things. So the first couple of years were materials general engineering, and then we moved on to a little bit more understanding on the aerospace side.
So yeah, it's always important to have that sort of practical focus in the mindset. So okay, so we've got our sort of design criteria, I suppose, and so we thought about you know, what application we're doing and maybe selected some particular properties. What's the sort of next thing we might do, having sort of defined the problem?
That's my favorite step. It's how we translate those properties to what we call microstructure. So microstructure is what defines the properties of a material. Basically, the smallest components that make up our material are basically what are going to govern our properties on the macro scale, right? So we build materials an atom at a time, quite literally. And how those atoms assemble themselves on the nano and micro scale is what allows us to tailor the properties in different ways. So I can put maybe 10 atoms of chromium, for example, in steel, and suddenly it becomes a stainless steel, right? So those little sort of architectural structures, one atom at a time, build up our microstructure. And the microstructure is what allows us to get our compromise of the different properties. So we can make a material stronger, we can make it more ductile, we can make it harder, more rigid, whatever it is that we needed to do, whether we wanted to conduct more electricity or not in some cases, or whether we wanted to be very resistant to high temperatures, for example.
And I think this is one of the things that, coming from a chemistry background, I hadn't fully appreciated in material science, was this importance of this thing that you call microstructure, and actually understanding at every length scale the material. So often people at school will have studied, structures and thought about it in terms of solids, liquids, gases, atoms. They'll have seen chemical formula possibly for, and a particular chemical structure of a material, something like salt or something like that. But that sort of level that we're talking about is really, really small. It's sort of a 10 billionth of a meter in sort of length. So if you were to line up 10 billion atoms, they would form the length of a meter. But going then up to the next level in sort of length scale is something that I think a lot of people haven't really thought about, that sort of the microstructure. So here we're talking sort of on the millionth of a meter scale, right? So we're talking about like 1 in a million. So if we were to line up a million objects along a meter rule. And often I don't know how you think about this, but I sometimes think of it in terms of like Lego blocks or something like that, and things sort of fitting together.
That's right. Yeah, that's a really good analogy.
The different structures then affecting different properties. And if you were to have like different shapes of Lego blocks, it will give it sort of different strength and...
Or how much space you have between the blocks. And
how do you go about logically choosing what to start in? Obviously, originally it'll be a lot of trial and error to get into, find out what you need to do. But obviously now in our age, well, how do you go with a logical step to do which material to put in or how to change the microstructure to get where you want?
That's a really good question. Thanks, Kavi. Yeah, so there are a lot of rules that we know empirically. For example, if we want a material to be very ductile, we know that if we make the atoms arrange in a very particular crystal structure, in this Lego blocks, for example, we know what Lego block arrangement will be most helpful in keeping the ductility. It doesn't mean that that's the best one, but it's a good way of starting out and sort of examining where we can go from there. In addition to that, we have a huge amount of modeling techniques that we can use now. We've learned over the years, and we started investigating the physics, because at the end of the day, it does come down to physics and how the atoms arrange with each other. So we can start using physics-based models to help guide our understanding of it. For example, this idea of adding chromium to iron that has been around empirically for years and years and years, they never really understood how that helped until we got into electron microscopes and we discovered how we can actually examine the material down at the microstructure level. It kind of worked, and it was really good that it worked, and it was kind of serendipitous that it worked. But we didn't understand why it worked until fairly recently, realistically. So now that we have that understanding, we can start building on it with different models that we can then accelerate the way that we can make those decisions on what the microstructure should look like. And there's a lot to learn still.
And those models that we're using, as you say, they're sort of, there are lots of different models out there. Some are more physics-based, some are more based on sort of just observing results and using things like machine learning in order to help interpret it and understand what's going on. But very often we then have to sort of, repeat this process over and over again. We use our model in order to create a material, but then we need to test how good that model is, because at the end of the day, it's only a model, right? We have no idea if it's going to give the right answer. And so we then have to push the material through and test what's going on, which I think is then sort of the next stage that we go through in the materials design process, actually, making the material and see what's going on.
Yeah, absolutely. We can run all the models that we want, but until we actually make and test something, we won't know what the answer is. So there's a lot of experimentation that goes on. And as you say, machine learning is starting to help us to accelerate those processes and run those models a lot faster, and artificial intelligence is coming in. But at no point will they ever sort of take over from experimentation alone. They might help us reduce the number of experiments that we want to do, but we need to make materials and we need to test materials. And it's a great way of also getting an understanding of the manufacturing of the material as well, because we can make materials and we can have an idea of how we want the chemistry to look like, but actually how we make something and how easy it is to make it is very, very critical to whether that material will be successful. I think Matt probably has some really good insights on making some materials that are very difficult to make.
Yeah, some of these materials that I've been making are quite hard to make, going through arc melting and then trying to balance the amount that you want to get out in the end, with some of them volatilizing and just flying off elsewhere in the machine. It's a hard balance.
Yeah. So when we're making one of these test materials, so let's say we've gone through we've spoken to the engineers at whatever company, we've chosen our properties, and then we've done some models and we've predicted a particular composition that we might want to experiment with, and then you're melting it up. So what sort of how big is this sample that we're making up in terms of, mass or size, or just to give people an idea?
Well, at the moment I've been doing about 100, 150 gram samples, so quite small.
Yeah.
And then when you want to bulk that out to actual production stuff, it's going to change the microstructure and everything even more. So you got one challenge in producing it in the small, and then you got another challenge when you want to bulk it out.
We're starting with small pieces, and then, as you say, scaling up. But that scale up comes with its own set of problems associated with it. You mentioned something, arc melting. Can you just tell us a bit about exactly what arc melting is and how it works?
Well, it uses an arc produced from electrical current. So about 200, 400 amps is typically a good range of what I use. And it produces a high temperature beam that you kind of direct at all of your components in an evacuated chamber, so that you don't get any oxidation or any unwanted substances, really.
Yeah. So, and you mentioned volatilization, I think you mentioned earlier, which is the loss of various elements. So one of the challenges is sort of making sure that composition is exactly what you expect it to be.
Yeah, so when you have a load of different components going in, they've all got different melting temperatures and boiling points, and sometimes they can cross over. So you've got to do a balance of melting them without boiling off other elements. And sometimes those melting points are higher than the boiling points of other ones. So it's a hard balance to strike, really.
Yeah.
And how often is it that you get the composition that you actually want?
I think I've been quite lucky in getting relatively close in the compositions, but if you want to go within like half an atomic percent, it is very difficult.
So it's often, if you look at, sort of industrial materials and things, there'll be a range in these things in order to sort of account for the fact that, there might be some loss of various things along the way. But as you say, it can be challenging, because I often, a very basic way of thinking about it, but thinking about like cooking and things like that, you're trying to put together a recipe for how to make this. And as you say, you've got these challenges associated with things at different melting temperatures and what order to combine things. And, you can completely mess things up if you do it in the wrong order, and end up losing half of your material along the way. So yeah, so we've taken our thing, we've melted up, and now we've got a small bar or small puck or some sort of small object, a blob possibly, and so what might we then do with it? What's the next stage in the process?
Yeah, so then we go into testing. So we can do a lot with the material, that small amounts of material, like the amounts that Matt's been making. We then need to define what kind of tests we want to put the material through. And that depends very much on the properties that we wanted to design it on. So we might want to test its strength, for example, at room temperature or at high temperature or at very low temperature. We might want to test its conductivity. We might want to actually find out what its melting temperature might be. Because sometimes when we make new materials, we might not necessarily know what that is either. So there are all sorts of different tests that we can do that we can then also compare to our models and see how accurate our models might be. The other critical thing that we do with all of these is also explore how we might be able to change the microstructure. So when we make something, as it comes out of whatever method we made it from, it doesn't mean it's going to stay in that format. So we might want to check, does the microstructure change, for example, when we put it into operating conditions? That might be high temperature, might be very low temperature, for example, or it might be high pressure environments, or it might be something else. So we might want to see how that microstructure, how stable that microstructure is, and what other ways we might be able to use to modify that microstructure. Like a cake, it's not a really good cake until you baked it, right? So that's a method that we use quite a lot to stabilize that microstructure, baking our material. And that we do for a lot of things. For example, you might want your wood to be dried in a kiln, right? We do that for metal, but our cooking temperature might be 800 degrees Celsius, 1,000, 2,000 degrees Celsius increasingly. The same with our ceramics. So that cooking time is also quite critical for materials.
And what sort of timescales for some of these things?
That's a question that is difficult to answer because, again, it very much depends on our applications, right? So we might want to cook it long enough to see how we modify it for service, or we might want to cook it for longer to see how it might behave in service, right? So if we want something to be viable for a manufacturing route, we probably don't want to be cooking it for longer than a day, right? Because we want to get it into service as quickly as possible. But if we want to test how long it's going to last at a particular temperature and how stable that microstructure is, we might put it in a furnace and forget about it for about 6 months or longer.
And that's, I suppose, one of the tricky things with sample testing is that, some of these things, if we're talking about a service alloy that's going to go into an aerospace component or something like that, it's got to last for years. Or I take, I suppose, an even more extreme example if we're talking about radiation damage for when we're storing radioactive waste and we need to consider how it's going to be stored safely underground for potentially thousands of years. And I suppose one of the sort of difficulties or complexities with sample testing is working out what the correct sample testing in order to understand the environment is that can still be done in a reasonable amount of time in a reasonable way in the lab and things. So.
That's very, very true. And we've got the models that we use to design materials. We can refine them using experimental tests that don't need to last that long. So you
mentioned materials lifing earlier.
Exactly. So, So we can use the critical properties and we might be able to measure something over a shorter life cycle, I guess. So a shorter amount of time, but then extrapolate it out to what the lifetime of that particular component might be. So we've got lots of different tests that operate in that way, where we can accelerate effectively the damage on the material using artificial methods that don't necessarily occur in nature that quickly. But we can do that sort of accelerated testing for a lot of materials. And nuclear is a classic example. So storing nuclear waste or even nuclear reactors that we don't necessarily have the luxury of putting something in a reactor for 50 years and then waiting to see what happens to it. We do that now, but 50 years ago, when we were building the nuclear reactors, we didn't have that knowledge.
No.
So material science is all about not wasting information. So everything that a material has experienced is something that we can use to help us build those models and build those models better.
And that's currently what I do right now. With the example of nuclear materials, instead of waiting to radiate your material for 50 years, I use an analog of cold rolling. So I cold roll my samples. I flatten out my material at room temperature, because if I do it at a high temperature, I reduce the amount of damage. It anneals the damage, it reduces the amount of damage in my material. So I do it at room temperature, so the damage stays within my material. And I cold roll it to different levels for different levels of service. So it's an analog for different types of time within the nuclear reactor. So that's similar what I do to speed up time. And that only took a day to do instead of waiting 50 years.
Much more convenient.
Yeah.
So, much easier.
Yeah.
So, yeah. As well as testing the samples for the physical properties, what other things do we look at or test?
So our next section, which is it tends to happen at the same time as our testing, is understanding and characterizing the material. We call it characterization. That means lots of different things to many different people. So, for example, we might want to, going back to the Lego analogy, we might want to figure out exactly in what configuration did we manage to get our little Lego blocks in our material to arrange themselves in. So we would use, for example, a very, very big microscope. Everybody might be used to looking at a microscope, an optical microscope that you might have at school, that you can look at, I don't know, a centipede or something like that.
So there's normally bits of leaf and things like that we often looked at. Or maybe I think people used to look at cells and things of various sorts.
Yeah, blood cells was one that we had a lot of, actually. Those but actually, in material science and engineering, we use what are known as electron microscopes. So we use the electrons to help us actually focus at a much, much finer resolution and magnify the material up to sometimes 1 million times magnification. So we can look really down to how those atoms arrange themselves in particular columns. In addition to electron microscopy, another really useful technique that we use for characterization is diffraction. And diffraction is sort of giving us an idea of how the materials are, how those little Lego blocks are separated from each other. And that's an area that has huge potential in helping us understand the microstructure of the material. But also it has huge potential in letting us understand the material while we're testing it. So it's one of the only methods that we can actually both test and characterize at the same time. So we can put something at really high temperatures and just watch it evolve, basically, which is really helpful and very, very useful, which is an area that
I was going to say, this is where I need to contain myself and stop myself from getting too excited. But we'll have an entire episode talking about characterization later on in the series, so I will contain my excitement until then. But yes, looking at these things, I still find it incredible that we're able to, as you say, explore those materials and look at those materials as they're undergoing that process and see what's taking place and that evolution. So really help create that strong link between underlying structure and physical properties and the sort of developments that are made there. So moving on then from characterization, thinking about it. So once we've made this material and we've tested its properties and we've found that it's fantastic for whatever purpose that we want it to be for. Matt mentioned earlier that we then have this problem of sort of scale up and thinking about going up a level. So we've made a small, a little bar of our metal or a little chunk of ceramic or whatever it is that's, a couple of centimeters big or whatever. But when we're thinking about, making things on an industrial scale, we could be talking kilograms and meters of the material and things like that. So we then have to think about that sort of scale-up process and how we go about making those things. So how does sort of our understanding of manufacture and things sort of link into this?
Yeah, manufacturing is an actually massive problem for material science and engineering. We can make things really, really nicely in a lab. We can control everything. We can wear a nice sort of suit when we're making our conductors or something like that so we don't contaminate anything. But that's not necessarily very feasible in a normal industrial manufacturing route. So that's something that is becoming more and more prominent that we take into consideration in the material design cycle. But traditionally, we tend to decide on our chemistry and then fix our manufacturing, which is not the most ideal way. So, for example, in an industrial setting, we might not be able to control to exactly those 10 chromium atoms in 100 of iron. We might get 12 or we might get 8. That's okay. So we need to start thinking about how we can design the material to be tolerant to those changes. So often we will see in an industrial scale-up a range of compositions rather than a given composition, which kind of helps us achieve the properties, but give us a range of those properties that might be in. The next key thing that we need to look at is how we control that microstructure. So we might control the composition and the chemistry of the material, but how do we control the microstructure? How hard we hit something, for example, when we're forging it, is going to change the microstructure. So we need to do some manufacturing trials that will help us understand how it's going to behave in the scale up. And we can do that on a small scale as well, right? So we can hit something with different forces and for different durations of time, and that will give us an idea of how the microstructure evolves. Or we can do those cooking trials we were talking about and how long we put things in an oven. Okay, this might be an oven that's as big as a building, but that's fine. We can also simulate that at a smaller scale. So all of those challenges that we start facing in manufacturing actually come down to us being very clever during the design cycle and learning as much as we possibly can about the material through that characterization. And then we can start building on those. And we can start combining understanding together through those models as well.
Because I just... coming back to designing for properties and things, it's there's a balance, I suppose, between these things about, if we're designing something that's very high temperature resistant, how on earth do you then melt it in the first place and things? How do you make the thing in the first place? And actually now, as we there are increasingly creative and novel ways of manufacturing things that are being created, and as the application becomes more complex and we require more complex geometries and things like that, we're increasingly seeing advancements in manufacturing techniques in order to give things that have a particular shape and things like that. I wondered if you could talk a bit about some of those more advanced manufacturing processes that we often come across in material science.
Yeah, we've been coming into quite a boom of manufacturing processes actually across all the different types of materials that you can think of, from ceramics to metals to even the biomaterials that are manufactured at very different conditions than traditional manufacturing processes. For example, one of the biggest advancements of the last 10, 20 years is additive manufacturing. Traditionally, we tend to make a lump of metal and then we machine things out of it. So we take a very good cutting tool and start cutting our lump into shape, a bit like a sculpture, right? If you have a lump of marble and then you make Venus de Milo. We can do the same using metals or ceramics or anything.
I don't have the skills to make the Venus de Milo, I'm afraid. My artistic ability is not up to that.
Right. We can get somebody else that can. But additive manufacturing kind of turns that on its head. Rather than taking a lump of metal and taking material out of it, we're actually printing material to the exact shape that we wanted it in the first place. So
additive manufacturing is what most people might more commonly have come across as 3D printing.
That's
right?
exactly right, yeah. So 3D printing. So you can use things like a fine powder of material. Often we do that with metals. We will use a very fine powder of material. And then we put that down and run a laser over the shape that we want, and then put another layer down and run the laser over it again and again and again and again until we have that 3D structure. And then we remove the loose powder and we're left with our Venus de Milo without having any chiseling. So your artistic skills don't need to matter anymore.
That sounds marvellous. Although I will have to learn how to control the computer to get it to build the appropriate shape. So, I suppose I need to brush up on my computational skills instead and things. So, yeah, I suppose that brings us to almost the end of our materials design. So we took our concept, we've predicted what we might want to get, and then we've made up a small amount of sample. We've tested it, we've characterized it, we've tried building it in various different ways and things. And so I suppose then it's time for the material to go out into the big wide world and go into a real application. But what does that mean then in terms of, because we need to think increasingly in the modern society about what happens towards the end of life of materials and things like that. So how much do we consider with those sorts of aspects, thinking about sustainability and recycling and the bigger picture and the bigger backdrop in which we're making these materials and things?
Yeah, that's something that's become particularly important as we are moving towards that 2050 zero carbon target and all of those big environmental goals that we have. There's a lot of things that we need to do even after we've manufactured the material. We need to understand, as you say, how we're going to treat it at the end of its life. And there's a lot of different ways that we might be able to extend its life, for example, as well. So there are repair technologies that we're working on that allow us to do exactly that, repair the material so that we can extend its life in service a bit longer.
So things like additive manufacture in order to sort of repair bespoke parts. And
that's right. Yeah, we might want, I don't know, we missed a tip out of a particular component, so we can rebuild it without really having to remake that component. Or we might be able to take the material at the end of its life and remelt it back and recycle it almost into a new component. Often when that happens, we tend to put that material into a component that doesn't have quite the same properties. So we end up with something that's degraded in the way that we think about that material. So we might have designed it for an aerospace component, for example, and we end up seeing that material at the end of its life in an automotive component or a drinking can. That's often the case for aluminium. Or key rings, that is often the case for aluminium as well. So we see that quite a lot, and that's something that we need to get better at. So recycling of metals that have gone into service, or really any component that has gone into service, is really difficult still, because we have these targets that we need to meet. So one thing we didn't really talk about is qualification of a material. So we might have made a material, but in every single industry, there will be specific testing that we need to perform. That's almost like a pass-fail test, like when you're testing your fire alarm at home. Does it work or not? So that pass-fail test we also have to do for materials. But there might be 10, 20, 30, 100, 1,000 different tests that we need to pass-fail on, and our material will have to pass all of them. So in some cases, what we see with the recycling challenge is that it might pass 90% of those targets, but not the remaining 10%. And is that a matter of the material, or is that a matter of our targets in the first place? So there is a lot of work going on to understand how we can refine both the targets, but also understand how we can use the recycling material in better ways.
And adding on to that is, like you always say, we're talking about the design cycle as in going back around to it, talking about the recyclability of it. There's also legislations that now go into the initial design process. So how 50 years ago when we created nuclear fission, we didn't have legislation about radioactive waste and what we do with it afterwards, after the post-cycle. Now with nuclear fusion, we have it where the material waste can't last more than 10 to 100 years in the ground, the half-life of these materials. Therefore, we have to put that into the initial side of it as well. So that helps with the recyclability.
I suppose there's also a scarcity of resource things, and some of the materials that we might want to use or some of the raw elements, I should say, that we might want to use are incredibly scarce. And so being able to extract them and things like that. But I suppose with all of these things, if you're talking about like extraction and recycling and things, well, and with the entire materials design process in general, there's an energy associated with, all of this heating, preparation when we're doing the manufacture and things, heating, rolling, like shaping and all of those things. And I suppose one of the other things is trying to work out how we can reduce those effects while still creating a material and a component that's capable and able to withstand the conditions it needs to be able to withstand.
Completely, yeah. And there is a whole area of science that's sort of between science and social science in some ways, called life cycle analysis, that lets us understand our carbon emissions or any other type of emissions throughout the design cycle of a material, or in most cases, actually, the design cycle of a particular component, so that we're looking into not only how we make the material and make that component, but also that component in service and at the end of its life, and all the way through its life cycle, effectively. And hopefully you will have an expert in life cycle analysis that's going to talk a little bit more about it in future episodes.
Indeed, we're going to talk about it in a future episode. So one thing that I thought it might be worth pointing out, because this was something that sort of blew my mind, or something that I hadn't really considered. But if I today sat down and said, I've come up with a brand new material and this is the best thing since sliced bread or whatever for X application or whatever, can you just give us an idea of the rough timescales that are involved between sort of with this whole process between now and ultimately it ending up, in a building or in a submarine or wherever it's going to end up, that material? What is that timescale that we're talking about? So.
Usually that's between 15 and 20 years. And that very much depends on those qualification tests that we talked about earlier. putting that material through every possible test to make sure that it's safe can be a very time-consuming task. And a lot of those tests we will have to repeat many, many different times to make sure that we have all the data that we need so that, for example, we can life that material properly. So you can imagine that if you're putting something in someone's body, like a hip replacement, you definitely don't want to take that chance lightly. So you need to make sure that that material is going to go through all of the approvals that it needs to. The same with a nuclear reactor. You can't afford for that to fail. Or an aeroplane component. And we have to do that very, very carefully. The other part of this that's a little less scientific and a little less, I guess, honourable is IP, right? A lot of cases, a lot of companies will want to secure their rights to that material and how to use that. And if, for example, you decide on a new material and you want to patent it, well, that's at least going to take you 3 years.
I was going to say, I think people often have heard of like pharmaceutical patents and things, but they're not really aware that, you know, you can patent a metal, for example, or something like that. It's something most people are sort of familiar with. But
patent a chemistry, you can patent the manufacturing method. You can patent the chemistry and the manufacturing method together. And those can be 3 different patents, right? And all of that takes a huge amount of time because, well, bureaucracy, right? So everything adds up, and that gives your sort of from design to actual service can be up to 20 years. We are trying to really bring that down, and there are ways that we are trying to work with, for example, qualifying bodies and accreditation bodies to make sure that we don't have to wait that long. But the key thing that we can't compromise on is safety.
Yeah. So one thing that we've sort of been referring to throughout this is we've called it a cycle. And so far we've gone from sort of materials design all the way to it being used and thinking about some of those wider concerns and end of life and the sort of bigger picture. But then I suppose how do we go back round again with this cycle? How do we get from there where we've got a something in service to starting the whole process again?
All of that information is really critical on how we're going to make that material even better in the future. So we might have made our nuclear reactor out of a particular grade of stainless steel, right? But we figured out, actually, if we made it slightly better because we've learned this, that, and the other, it will be lasting even longer. All of that helps us improve our models, for example, and our predictive capabilities. It helps us understand that component, that material, and how we manufacture it better. So with every iteration of that materials design cycle, we will make things better for the next one, right? Often, the minute we put a material into service, it's often out of date already, right? Because we've decided that actually we've learned so much that we will only make it better the next time round. So for example, some of the work that I was doing during my PhD, it's now coming towards realization and is going to go into service in the next 5 or so years. Right?
That's very exciting.
It is. But we started the design cycle for the next material 5 years ago.
Yep.
So already we knew we were going to be out of date and that jet engine will need to meet some new and more exciting requirements. And we knew that we could make it better. So starting that cycle, we often start that cycle before we've even finished the last one in the majority of cases.
And I think one of the things then with sort of material science in general is it comes back to something we were talking about right at the very start, was there's this sort of, well, a lack of understanding about what material science is, but also a misconception, and particularly with metallurgy, which we've been focusing a lot on today and which we'll use as a sort of case example going forward in the series. There's this sort of idea that, you know, we know everything about it already. Metals are old. You talked about the Iron Age and the Bronze Age and things like that. But actually our understanding of them is still and continuously developing and iterating through this cycle again and again, repeating going forward.
Absolutely. So the Bronze and the Iron Age, there's just 2, maybe 3 elements on the periodic table. That periodic table is quite large and there's quite a lot of areas that have been completely unexplored for us. So Matt, I think, mentioned high entropy alloys. So I was going to ask him to actually go into a little bit more detail on what is now one of the most widely researched areas in metallurgy over the last sort of 10 years or so.
Yeah, so, I mean, you've got your conventional alloys that, if we think of a 3-part alloy, so iron, nickel, and carbon. We kind of stick, if you picture that in a triangle, one element at each corner, we kind of stick to the outsides of that triangle. We want one major addition with two minor additions, really. But for high entropy alloys, it's kind of a equiatomic mix of all the elements. So we're kind of exploring that middle area of the triangle, which has left a largely unexplored area. And we've found some materials that can produce some fantastic properties within that space, which is why we've got all this interest now.
Because picking up on what you were saying right at the beginning, Kathy, is that, very often we start with a material and gradually sort of step our way towards something. So, we start with, if we talk about alloys in general, people will talk about steels, which is iron with a little bit of other stuff mixed in, or nickel alloys, which is nickel with a little bit of other stuff. But here we're going, as you say, we're going, what happens if we mix, everything together in a melting pot and see what happens, which is incredibly exciting. And it means there are lots of different directions that it can be sort of pulled in, investigated in, and even you're in your second year of PhD now, Matt, and you've been looking through the literature and things, and you've seen, I'm sure, lots of different sort of applications that people are sort of pushing towards with these different materials and things.
Yes, there's a huge amount of applications with the high entropy alloys. You've got at least what I'm doing is the excellent radiation tolerance. You got high temperature applications, so potentially rivals superalloys. You got your high strength. You even got the low temperature, extremely low temperature capabilities as well.
Yes, there have been some recent studies looking at sort of cryogenics, those very cold temperatures, and the superalloys, which you mentioned before. They're a particular class of material that are often used in aerospace, and we're potentially looking at replacing them with this new generation, assuming it works and can get through all the tests and everything and the qualifications and everything that we've been talking about so far, and making sure that we can make those materials which are safe. But it's very exciting to see this sort of new area of sort of metallurgy and a new direction to sort of push and explore in, and finding those new properties.
It is, yeah. It's a great area to be in currently, and there's so much we don't know. I think that's you touched upon it earlier. We know very little. Less than 1% of what we know is actually out there and in use. There's so much that we don't know, and there's so much that we do know, but we can't actually use yet. So there's a huge amount of potential on how we can make things better.
Yeah, that's fantastic. Kathy, is there anything else that you think, our listeners should know about materials design, the materials design cycle, or just material science? Something you wish you'd known when you started your journey in materials, or anything like that?
Yeah, I think not taking your own empirical understanding for granted, I think, is the best advice that I was ever given, to be honest.
So that empirical is the sort of trial and error type.
Yeah, that trial and error and that sort of gut feeling or things like that, they're not necessarily true. The majority of our sort of advancements in metallurgy are all entirely by accident. Oh, no, I was melting this metal and accidentally I knocked in some chromium. Oh, no, here's stainless steel, for example. Some of the materials that I've been working on were also a typo most of the time. I accidentally added an extra element that I wasn't anticipating. And suddenly, it's way better than anything else I was depressed for months to now. Turned out brilliant. So be open to lots of new ideas and be open to experimenting with things, because at the end of the day, that is our job. Yeah. We are scientists and engineers. We need to try lots of different things. And we shouldn't just think that we know everything.
Yeah, it's exploration, exciting new spaces to explore and things. So yeah, that's fantastic. Kavi and Matt, have you got any other questions for Kathy about anything that's been said, or anything that you wish you'd known about, material science or the material science design cycle when you started out?
I mean, it's not something that I wish I knew, but it's wish I knew about earlier, and it's just like how interesting and amazing the microstructures of materials can look.
They're so pretty. Some of them are so pretty.
The EBSD maps are some of the prettiest things. And then I worked on a material that produced some nanowires, and looking like the jungle of nanowires is just amazing.
EBSD is a particular type of characterization which produces very, very beautiful images. We'll put some up. I'll put a link in the show notes so you can have a look at some of these beautiful structures and things that are created in some of the materials. And we might talk about EBSD in more detail in a future episode. So how about you, Kavi? Any other thoughts?
Going on to what Kathy said about going with the trial and error, being open about something, everything is like what I've kind of learned is I thought I was going in one direction and things just go in a completely different direction. You have to be open to that when you go into the material cycle, the design cycles, especially when you're doing a PhD.
Yeah. I think it's the nature of research. When you're at school or even undergraduate at university, the practicals that you do are very much, you mix A and B and it makes C and it works. And you then get to research and you go, oh, I'm going to mix A and B together, and seldom does it make C. And normally something unexpected happens, which can be good or can be bad. It depends. And then it's about sort of, working with that process and sort of evolving and discovering more.
Definitely, because everything up to college is a straight line.
Yeah. So material science is for the win, I suppose.
It's a sketchbook.
No, a straight line degree.
I think material science is just like sketch where you just go on and draw things, and then things just mix together to make a pretty picture towards the end. So
yes. Well, thank you all for our chat today and talking a bit about the materials design cycle. So in this podcast, in the next few episodes, what we're going to do is we're going to take each one of those sort of areas that we've been talking about today and go into a bit more detail about it. So thinking about things like defining the problem, materials prediction, making the samples, advanced manufacture, characterization, sample testing, and then the big picture, thinking about sustainability, recycling, storage, and all of those sorts of things. So hopefully, over this podcast series, we'll get more of a chance to explore some of the things which we've only touched on in very lightly in this episode. But for now, let me thank my guests. So thank you, Kathy, for joining us.
Thanks for having me, Lewis.
And Kavi and Matt, thank you for joining us as well.
Yeah, thank you very much.
And to our listeners, thank you very much for tuning in, and please do join us next time when our topic will be defining the problem. Thanks very much for listening. If you want to join the conversation, you can find us on Instagram at Materials Unlocked. If you want to find out more about the topics that we've covered and the work that we do, a link can be found to our website in the show notes. Our thanks to the Advanced Metallic Systems CDT, the Henry Royce Institute, and the Department of Material Science at the University of Sheffield. See you next time.